So yeah, I'm going to talk about Radicle, but also slight difference to the proposed title, which is that I'd like to talk actually about some of the fundamental ideas behind peer-to-peer systems and how this kind of applies to Radicle and kind of look at it through that lens. But hopefully it's also useful for people building peer-to-peer systems or thinking about doing that. I'm sorry if you can't read the font. I'm sort of experimenting with this this new software. Anyway, so I'm Cloudhead, and I work on free software. I'm kind of a peer-to-peer maximalist. I think everything should be peer-to-peer, ideally. And I co-founded Radicle 5 years ago with Ellie, who's also in the audience. On the side, I sort of work on Bitcoin light clients. So I'm big into light clients. Yeah. So first of all, what is peer-to-peer? I think it's important to define at least how we're thinking about peer-to-peer at Radicle. And the idea is pretty simple. The word autonomous was mentioned by Stellar Magnet, but yeah, essentially every user is sovereign and has full control over their experience. I think that's kind of where we're starting from, or what we're trying to build. And this has several implications. One of them is local first, which again, people have been talking about, but I think of it as sort of a necessary consequence of user sovereignty, because essentially, if we didn't have local first software, then it would mean that people are relying on each other to provide services or data or whatever. And then, of course, every user has to run the same software. And another cool thing is, as long as there's a user, there's a system, right? So you can, a peer-to-peer system should be usable by a single user, essentially, on their own. They could be like the last man standing. And fundamentally, peer-to-peer networks are untrusted because, again, people cannot really trust each other by default. There's two types of peer-to-peer networks. Radicle is what's called an unstructured peer-to-peer network, but there's also structured ones. An example of a structured network would be like a DHT. Whereas an unstructured network would be something like secure scuttlebutt, where you pass messages by gossip and there's no real topology. I think also like a true peer-to-peer network is unstructured, in my opinion. Again, because you can't really rely on nodes doing a specific job or specific role if you want your network to really be resilient, and you really want every user to kind of be in control of their node. So what are the benefits of peer-to-peer? I think three key benefits: security, censorship resistance, and resilience. So security is all about verification. Censorship resistance, and interestingly again, this would be filter resistance if we're going to that terminology. And then resilience is just basically the network needs to keep on running no matter what happens. You'll see I don't have privacy on here. I think privacy is, of course, it's great to have, but it's a bit at a conflict with other peer-to-peer benefits, because your data is basically ending up in all kinds of places and on all kinds of nodes, and so it becomes really, really hard to have both privacy and well, these properties. So how do we build a peer-to-peer network, and how is Radicle built? So you start with a node, and then essentially what the node is that it's kind of transforming a network context into a local experience, right? And the network context is untrusted, the local experience is trusted, so basically everything that's on your machine you can trust, everything that is not on your machine you cannot trust, and the job of the node is to kind of make that transformation by verifying data. How do you make it local first? At least the way we do it, which I think is pretty standard, is essentially you put a piece of storage between your applications and your node, and that's kind of what we're calling local storage. Everything in there is trusted, and your application only interacts with that box, essentially, and the node puts things in that box, right? And that way you kind of, the node doesn't even have to be running. It can run opportunistically, it can start and stop, but your application always works because it's working off of local data. And how do we make it work? So this is kind of the hard part, right? Like the problem solving. So There's been a lot of really interesting ideas in the previous talks. I'm kind of going to go a little bit more fundamental and try to think about a few different principles. So the three principles that I think are kind of the most fundamental are trust. So how do you go from this untrusted network to a trusted local experience? Conflicts. So if nodes on the network are publishing data like concurrently, if you're building some kind of collaboration software like Radicle, you will have conflicts if you don't figure that out. So two people editing the same comment or opening and closing an issue or that sort of thing. So you have to have a solution for that. And finally, data availability. Yeah, you're in an unstructured network, and you don't have a server from which you can request data. So you have to figure out which node has what and how do you get that, right? So these are kind of some of the fundamental problems, and each of them has a bunch of different solutions that could potentially work. So starting from the problem of trust, it can be stated like without an authoritative source, such as server peers can forge data, right? So that's the problem. And the most basic primitive for that is cryptographic signatures, right, to solve that. You have a bunch of data, you sign it with a key, you end up with a data plus a signature, and then you can verify that. Of course, it needs to go a little bit further than that because public keys can be lost, and public keys don't necessarily give you much information about who the author of that data is, right? So you can combine that with decentralized identities and things like that. And I'll talk a little bit about what Radicle does for that. Then for conflict resolution, again, without a single source of truth, you have this problem of divergent state, right, or histories, and then you have to figure out a way to converge to the same thing, right, so that users see the same thing on their applications. And there's, again, a bunch of ways to solve this. Blockchains do it very expensively, but there's much cheaper ways to do it, like CRDTs and other data structures. And here we use Git a lot for this, and I'll also talk about it a little bit. And then finally, data availability. Again, no single source of data where you can ensure that things are always online. And even that doesn't really exist in a centralized world, as you know. And for this, essentially we use gossip and replication. So nodes kind of talk to other nodes about what they have, and don't have, what data they have. And they also talk about other nodes, right? So you exchange information about nodes and information about the data itself. And then when a node is looking for some specific piece of data, you can connect directly to who has it and replicate it and download it, essentially. So the next thing I'd like to talk about is how we're using Git as a sort of foundation for building our peer-to-peer system. And I don't know how many people use Git in this room. I suppose probably 50% or more, at least. And so Git is a version control system, and it's fundamentally been designed as let's say, a decentralized version control system. What that means is simply that it's sort of been designed so that every user kind of is always working off of local data, and then you kind of synchronize when you can with a server. But it has been designed with a server in mind, right? Even though it is kind of local first, and to an extent it's peer-to-peer, but I wouldn't say on its own it is. And Git is really cool for peer-to-peer systems because it does a bunch of things that we like and that we need. One of them is integrity checking, so it basically makes sure that data is not corrupted. It has a really nice native DAG implementation, directed graph, which is super useful for building peer-to-peer applications. It's a content addressable store, so like IPFS. Every piece of content has a content ID. It has built-in versioning, and it has a really efficient transfer protocol. So the basic Git replication protocol is kind of an interactive protocol which is much more efficient than just like FTP or something like that. But there are some problems. So, or there's things that are lacking, let's say. One of them is that it doesn't have a solution for data availability. So that means that it's just kind of like you have a Git repository, but you don't. There's no Git network. There's no way to kind of talk about what repositories a node has or doesn't have. It just has that at the repo layer, so within a single repository. It also assumes a trusted environment, right? So it doesn't have any kind of protection against disk flooding attacks and things like that. It has no concept of repository identity. So you can look at the state of a repository and look at a branch and its commit and stuff, but you can't. There's no sort of identifier for a repo that is globally unique and that can be used to know whether you have the right thing, the right piece of data. And then finally, it doesn't handle conflicts automatically. So there's ways to merge code with like merge branches, but there's no sort of there's nothing like a CRDT essentially that would work out of the box at least. So let's go a little bit more into actually how Radicle works and how it's built on top of all these principles that I mentioned and these ideas. So Radicle is essentially a stack of technologies. It's you can think of it as a sovereign code forge, a peer-to-peer protocol and data network, or Git's missing peer-to-peer networking layer, right? And so it's a stack of 4 things. At the bottom, there's the node, and we talked about nodes. On top of the node, there's storage, and this would be the local storage, so the local first storage. On top of that, you have repositories, and these are actually regular Git repositories. But we do quite a bit of fancy things with them to make them work in a peer-to-peer context. And then on top of the repositories, you have the application layer, which is essentially a CLI and a web interface, and also a TUI that's in the works. So if we start with the node, what the node does is that it creates a gossip network. So this isn't it's not an overlay network in the sense that nodes just kind of directly refer to each other via public key plus address. And it's essentially, it's a pretty basic flooding algorithm where you just talk to your peers, and they talk to their peers, et cetera, and information is disseminated that way. We use a noise handshake protocol, which is, well, it's a pretty nice framework for designing handshake protocols for creating encrypted streams between nodes. And nodes essentially, as I mentioned previously, they exchange data about inventory, so that's the repositories they have locally, and addresses of other nodes. And this data is gossiped across the network. There's also data like when a repository is updated, the Git refs or the branches are updated, that information is exchanged and disseminated. And then we use Git tunneled over the noise encrypted session to replicate data. And that's pretty cool because, again, Git is very good at replicating code and other kinds of documents. And so we kind of get a lot of that efficiency for free. Another cool thing about the gossip layer is that we use Bloom filters for subscriptions because since we're working with an unstructured network, every node can decide to host whatever repositories it wants, right? As opposed to a DHT where you would kind of host a certain shard of the data set. So the problem this creates is figuring out which nodes have what data, and if a node is hosting like 1,000 or 10,000 projects, you don't want to have to pass that list around the whole network, right? So you can use something like a Bloom filter, a probabilistic data structure to compress that. And then on top of that, we have the storage, and this is essentially, it's just Git repositories again, and that's how we kind of benefit from all of the niceties of Git. But on top of that, we have identities stored in there. So these are kind of the stable repository identities as well as user identities that are stored as refs and objects inside of Git. We have signatures that are also stored there that are, because Git has code signatures, but doesn't have signatures over entire forks of a repository. And since we have things like issues, pull requests, and things like that, which we call patches, stored inside of Radicle, we need to maintain signatures for those things as well. And then finally, it has what we call collaborative objects, and these are essentially our CRDTs that implement things like issues, patches, discussions, etc. Yeah, I'll talk about this a little bit in here. So collaborative objects are a really kind of neat way of representing conflict-free data structures in Git, and we do that by using what's called a Merkle DAG, which again comes for free with Git because it's really just a history of commits that can be merged with another history of commits without any conflicts. And so each peer essentially that is, let's say, participating in a discussion on an issue or a patch will have their own DAG or their own, actually they will have a linear history pretty much. And then when you replicate, you essentially merge all these histories and then you traverse them to render a final state. So this kind of gives you all of the benefits from Git fetching dependent data. So if you have a comment that is a reply of another comment, Git will fetch that automatically because we encode that dependency in the commit graph. And then you get the benefits, of course, of idempotence and everything, because Git will deduplicate comments and commits and objects. So yeah, and then another thing stored inside there's a repository are these identities, and they're self-certifying. That means that you can kind of start with, if I just give you an identifier that's kind of a short hash or public key, well, it's usually hash, you can actually reconstruct the whole history of changes of that identities just starting from that one hash, and in a fully untrusted way. So you don't need to trust anyone as long as you trust that that is the right hash, the right identity. You can sort of verify any change in the history, and so that applies for repositories, and that means that given a repository ID, you can verify the history of a repository as it changes over time. And finally, we have configurable data policies. So again, this is important in an unstructured network because each node decides what it's going to host. And so you need a way to configure that and to share that and to kind of make sure that users are in control of the data that's stored on their nodes. Finally, at the top, we have the application layer. Command line interface and a web interface. So Radicle, compared to something like GitHub, is a lot more terminal focused at the moment, at least. So the CLI is pretty full featured. You kind of are onboarded on the CLI. You create your identity, your public key pair, public-private key pair, etc. And then the web, the way that works is that it connects your local node. So there's a hosted web interface that you can connect to your local node, but you can also run your own web interface and connect that to your node. So it kind of authenticates with the node via like a session, like a token, and then that means that you can sign artifacts through your node, but using the web interface. And yeah, it all operates on local data only. And patches, issues, and code browsing are already live. They're working. They're not finished in the sense that there's things like inline code comments and things like that that are still in the works. But the collaborative objects are there. The system, Radicle as a protocol, was designed to be extensible. So you can essentially create other types of collaborative objects that will be replicated over the protocol and that do other things, like you can implement a wiki or a Trello board or whatever it is, and it's all going to kind of use the same underlying replication mechanism, verification, et cetera, et cetera. So it's quite extensible. Yeah, and that's basically it. You can experiment with Radicle today. You can go on radicle.xyz. There's a little thing you can copy, which will fetch the binaries. Currently, it's just Mac OS and Linux, no Windows. Windows is far future, probably. You can try it out. There's very little documentation, so do come on our Zulip, which is also linked from the website, to ask questions, ask for support. I'm also happy to do a demo for anyone who wants to check it out later. Thanks.